It's a pool of different ions, like cations and anions in seawater. Starting, of course, from chloride, we have a lot of sodium chloride.
Seawater also contains lithium, scandium, vanadium, gallium, indium, boron, molybdenum, and rubidium.
Basically, everything you can find on the periodic table is in the ocean.
That was Alex Ivanov at Oak Ridge National Laboratory, Heike Glada at the University of Bremen, and Chinmay Subin at Pacific Northwest National Laboratory. They are all scientists and engineers whose research takes a deep dive on an elemental elixir that most of us call seawater. You're listening to Stereochemistry. I'm your host, Ariana Remmel. In this episode, we'll talk with researchers from around the globe who are developing ways of extracting a variety of elements from the world's oceans. It's the next installment in our series about water and the ways it intersects with the environment, society, and chemistry. To tell us more about the future of seawater mining, we've invited C&EN Physical Sciences reporter and team lead Mitch Jacoby onto the pod. Hey Mitch, good to have you here.
Hi there, Ari.
So Mitch, the first thing that comes to mind when I think about the ocean is stuff like sunny days on the beach, swimming, vacation stuff mostly. But Alex, Heike, and Chinmay just spouted off a list of ingredients that makes it seem like I've been taking a dip in some sort of elaborate chemical soup.
Yeah, that's certainly one way of putting it. And I think that most people, even most scientists, don't go straight to metals, elements, and chemical separation technology when they're relaxing along the seashore. But there's a lot of stuff in the deep blue sea besides saltwater and marine life. And some of that stuff could one day power energy infrastructure all over the world. So today on the pod, we'll hear from scientists in the United States and European Union about why they're interested in extracting elements, especially metals, from seawater, and how they're using chemistry to do it.
Speaking of energy resources, my ears pricked up at a few of the elements in that first list, like lithium. We did an episode with C&EN business reporter Matt Blois about mining lithium from brines in the Salar de Atacama in Chile and El Dorado, Arkansas, here in my home state.
Right, that's because lithium is a critical material for making batteries and other electronic components that run today's tech world. Heike calls it white gold because it's so critical for our modern energy systems. And there are lots of other metals that make today's technology possible. Indium, for example, is used to make solid oxide fuel cells and high-strength alloys for aerospace engineering. Scandium, another transition metal, is found in television screens and solar panels. The ocean even has rare earth metals that power next-generation electric car batteries, and uranium, that's a critical fuel source for nuclear power plants. You know, those plants produce almost 20% of the electricity in the United States today.
But why look to the ocean? Aren't there easier ways to get uranium, like mining it straight from the ground?
Good question. That's what I asked Cerie Brown, who also works at Oak Ridge National Laboratory in Tennessee with Alex.
In the case of uranium, with the current consumption that the U.S. is using for the nuclear fuel, the majority of that uranium actually has to be purchased from other countries. About 80% of the uranium used in nuclear power plants in the U.S. have to be purchased. Terrestrial sources of uranium may run out within about 100 years.
So it's a matter of long-term national energy security. Most of the world currently gets its uranium from Kazakhstan, Russia, Uzbekistan, and Australia. But as Cerie said, those land-based sources, mines, they may run out within a century.
So that's the situation with uranium. What about the other elements used for electronic devices?
Other energy-critical elements are in the same boat, so to speak. For example, around 95% of the world's supply of indium and scandium comes from mines in China.
Okay, so let me make sure I've got this right. These various metals and minerals are important for energy security and for computers, electronic devices, and all the high-tech gadgets that we depend on for just about everything in the modern world. But there are only a handful of countries worldwide with terrestrial mines that source these critical minerals.
Right. Some of the people I talked with are at U.S. national labs, and others are part of a large European Union project called C for Value. That's spelled C, S-E-A, the numeral 4, value, C for value. The countries funding this research want to ensure that there's a stable and ample supply of energy-critical elements, a supply that isn't affected, for example, by political or economic instability outside of those countries' borders, and that's why they're trying to extract them from seawater.
Ah, so we are back to the high seas. Just how much of these metals is actually in the ocean anyways?
A lot. Here's Suri again.
The amount of uranium in the seawater is about 1,000 times of the uranium from terrestrial sources.
Wow, so you're telling me that there is 1,000 times more uranium in the world's ocean than in all the land sources combined?
Yep, that's exactly right.
Okay, well, what about the other elements you mentioned?
Well, because of the enormous size of the oceans, there's plenty of the other elements too. Like Chinmay from Pacific Northwest National Laboratory said earlier, just about every element on the periodic table is out there floating in salt water.
I'm guessing there's a catch.
There's a huge one. Here's how Chinmay put it.
Some of the elements, say sodium, magnesium, calcium, potassium, and things like that, they're in much higher concentrations. But the oceans also have lithium, rare earths, and all the other energy critical elements that we might be interested in extracting. But the challenge is they're in much lower concentrations.
Oh, sure. That makes sense. But how dilute are we talking here?
That's what I asked Alex.
When I talk about uranium extraction, so students always asking me, so where is this uranium located? I've never seen uranium in seawater when I go to the beach. So, but it's there. All kind of valuable metals, transition metals, and uranium are all there, but you won't see them in their original form, like in the form of metal or even salt, because they're dissolved there. So they're present there at really low concentrations. In case of uranium, it's 4 milligrams per ton of water. Can you imagine? So this kind of very, very dilute concentration.
Wait, so is Alex saying that in a ton of seawater, that's 1,000 kilograms of salt water, there's just 4 milligrams of uranium?
Yep, that's it. But remember, there's a whole lot of water in the sea, so that number adds up.
Sure, but that dilution ratio makes the proverbial needle in a haystack sound quaint. How on earth do folks extract what is essentially a few specks of dust from tons and tons of seawater?
That's a very good and long-standing question. Alex gave me a primer about the history of this endeavor.
It all started in 1990s by Japanese scientists. And it actually can be explained because Japan depends on the imports from uranium more than USA right now. So if you look at geographical location of Japan, it's surrounded by oceans, right? So there is a great temptation to grab all this uranium and use for their needs. Maybe that's why they were the first one who provided the proof of concept for this technology of mining uranium from seawater.
He actually pointed out that there was an even earlier effort to mine uranium from the oceans by scientists in the UK, but the Japanese researchers went much further.
The first technology was a platform-based technology. So in this kind of technology, they processed this polymeric adsorbents into stacks, and these stacks were lowered into seawater, and the idea was that the ocean currents would move the stacks through the water, extracting uranium.
It turns out, though, that that way of doing things was too expensive and the uranium uptake was too low.
So they switched to another technology, braided fiber technology, where they produce these amidoxine fibers.
What kind of fibers?
Amidoxine fibers. Amidoxine is an organic functional group, a certain arrangement of carbon, nitrogen, oxygen, and hydrogen with a carbon-nitrogen double bond. People studying uranium uptake from water at that time examined a whole slew of functional groups, and it turns out that the amidoxine group is particularly good at snagging uranium in its dissolved form. That's the uranyl, or UO2, cation.
So the idea is that you immerse these braided fibers onto the bottom of the ocean bed and then attach them there. So there is a kind of radio transmitter attached to these fibers. And after a certain period of time, for example, after 1 month, it sends a signal to a ship to detach it from the bottom of the ocean bed. And then it floats back to the surface for a straightforward recovery.
So it's a similar strategy to the prototype that used stacks of polymer sheets to passively soak up dissolved uranium. Did these researchers notice an improvement with the amidoxine fibers?
They sure did.
they found that they can extract 1.5 grams of uranium per kilogram of adsorbent after 30 days of deployment. It was a landmark discovery because they kind of were saying that, hey, this technology can work. The only catch was just to make this technology financially viable. And that's what we've been doing.
So what are Alex and the other scientists doing now to improve on this technology?
Well, one strategy that Suri mentioned is fine-tuning the polymers, mostly acrylic or polyacrylonitrile, and the amidoxime functional group. It turns out that that group comes in an open molecular form and a more closed or cyclic form, and they don't behave quite the same way.
From what we and other scientists have found is that the cyclic structure actually grabs the uranium in larger amount than the open chain structure. However, even though the cyclic structure grabs more uranium, it likely grabs a lot of vanadium along with it too. So like right now, one of the movement in research is to get more selectivity towards uranium.
Yeah, that's a classic chemical separation conundrum. It's hard enough extracting uranium from the ocean without having to sort through whatever else the fibers sop up.
Exactly. Another research area is tailoring the way functional groups are positioned along the polymer chain. The Oak Ridge group and their coworkers found that some arrangements of alternating amidoxime and carboxylate groups work well together, mainly because of carboxylate's water-loving nature.
We found synergistic effects that not only the amidoxime group that plays a role, the carboxylate groups next to them also help push the uranium towards the amidoxime group better.
And all the fine-tuning of the polymer adsorbent has really paid off.
Right now, it went up to like almost 8 grams per kilogram. A few years ago, it was between 5 and 6.
Yeah, wow, that sounds like a big boost from those earlier devices. What about separating the uranium from the fibers? How do they do that?
Alex and Suri explained that the usual way is by treating the adsorbent with strong acids, then collecting the metal as a precipitate. That's another area of research people are working on nowadays, using milder methods and reagents like hydrogen peroxide and sodium bicarbonate. So that's where uranium stands now. The work is still in the research phase.
So regarding commercial use and industrial applications of these fibers, I think it's still kind of far from reality.
Alex is giving a pretty frank assessment. There are up to 8 grams of uranium per kilogram of fiber, but he says the target is more along the lines of 15 to 30 grams. Even so, he's pretty upbeat about it.
There is nothing impossible. Maybe we'll come up with some other functionality or even different technology for mining uranium, and we will be able to mine it from seawater in the future. So I'm optimistic about that.
Wow, that's really cool, Mitch. I'm excited to learn more, but let's take a quick break first. Then we'll continue our journey around the world to explore other strategies for mining precious elements from our planet's salty seas.
Hi, listeners. Did you know that C&EN has an app? I'm Rochelle Adkins, C&EN Senior Product Manager, and I'm so excited to share that our mobile app, Chemistry News by C&EN, has a fresh new design that makes it easy to read your favorite chemistry magazine on the go. All standard and premium ACS members get instant access to the latest news from C&EN right on your phone. With the C&EN app, you can bookmark your favorite stories, download entire issues, and you'll be the first to know when a new issue has been published. Chemistry News by C&EN is available for all iOS and Android mobile devices, so head over to the App Store now and search Chemistry News by C&EN. That's Chemistry News by C&EN. You can also find a link in the show notes.
And we're back. I'm here with C&EN Physical Sciences reporter Mitch Jacoby. So Mitch, what are some of the other ways scientists have tried to mine elements from seawater?
Right. So earlier we heard about how Alex, Suri, and their colleagues are developing materials that you lower into the ocean, where they passively pull out uranium from the water column. But out in Sequim, Washington, Chinmay Subin at Pacific Northwest National Laboratory is tackling the dilution problem head-on.
Sequim is actually a very small town It is a beautiful place with snow-capped mountains and oceans all in a very small area. And it's right near the Olympic National Forest.
So from scenic coastal swim, Chinmay discussed some big picture concepts about extracting minerals from water. One of them was about the type or the source of water used for this work.
There's large volumes of water that have to be processed. And we know that processing water, moving water, pumping water is all very, very energy intensive. So that's where being creative about how we extract minerals and what sources we use, whether we pre-concentrate it, becomes important.
Pre-concentrating the minerals? How does that work?
One approach is by taking advantage of desalination plants that extract fresh water from a salty stream of seawater. That process produces the drinking water that comes out of the tap for millions of people in the U.S. alone.
So when you extract the fresh water, what's left behind, the waste stream, is what we refer to as a waste brine or a desalination brine. And the brine has the same salts you start out with, but it's a bit more concentrated because the water has been removed from it. So the brine is a little bit easier to work with in terms of extracting elements that may be in low concentration.
So where are these desalination plants?
Everywhere. They're all over the world. A quick web search tells you that there are more than 16,000 desalination plants installed worldwide. That number may be a lot higher depending on how you count them. And when it comes to taking advantage of this existing infrastructure, Chinmay and her team at PNNL are in good company. I also spoke with researchers from a project in the European Union called C4Value. The brine from desalination plants is the starting point for all of C4Value's mining work. One of the researchers working on this project is Sandra Meca with Iracat Technology Center in Spain. Here's what she told me.
We want to develop a process capable to recover several metals and minerals. In conventional mining, the objective is to recover only one mineral or salt or metal. In this case, we want to recover up to 9.
To do all that, this EU C4Value project is bringing together 16 partners from Spain, Germany, Italy, Belgium, Ukraine, the Netherlands, Finland, and Switzerland to conduct fundamental and applied research.
We have a lot of universities involved from around Europe. We have also some companies that make research for technologies. Then we have also seawater desalination plants operator. Our objective is that desalination plants can be the new mines of the future.
Much like the work going on elsewhere, the C4Value research is still at the early stage, and because of intellectual property rights and so forth, most of the results aren't yet ready for public consumption. But Sandra and her colleagues shared a number of things. For example, one focus is boosting the concentration of the salts in desalination plant brines above standard levels, so that the subsequent steps, the separation steps, work even better.
Okay, so how do they do that?
Well, one way is by using better water evaporation technology in desalination plants, specifically re-engineered evaporator tubes to pull out even more fresh water and further concentrate the brine. That's Heike Glade's specialty at the University of Bremen in Germany. We heard from her at the very beginning of this episode.
Innovations for evaporator materials have not been made for years.
She says everybody uses metal tubes, but the high chloride content in the brine wreaks havoc on the pipes. So that means plant operators need to use corrosion-resistant metals that are expensive, heavy, and prone to fouling. So Heike's team is taking a different approach.
We are developing polymer composite evaporator tubes made of polypropylene filled with graphite flakes.
Polymers can bypass the shortcomings of metals that Heike mentioned, the high cost, high weight, and so forth, but they tend to be lousy heat conductors, which is really important for water evaporation. That's why they're doping the propylene tubes with graphite, a really good heat conductor.
Okay, so they're getting better at making super concentrated brines. What's next? Like, how do you separate the metals?
One strategy comes from Evelina Repo at Lappeenranta University of Technology in Finland.
In our group, we have created a new approach for these separation technologies. we have started to develop 3D printed ionic chains or adsorption materials. With this 3D printing, we can produce optimal structures that contain optimal porosity, and we can optimize the flow rates, reduce the energy consumption when we pump water to be treated through those materials.
The way Evelina explains it, they're modules, like high-tech filter blocks, each one customized for a specific metal. She says they'll be used in series in a flow-through device. The idea is that the brine is pumped through at one end, and as the solution passes through the modules, each one selectively pulls out one of the metals, producing a bunch of pure streams.
Okay, so this incorporates some of the absorption strategies we heard about from Alex and Suri, but with a different chelating substrate for each element, yeah?
Basically, that's the way it works, and Evelina's team is already testing their new setup.
We are getting good results already. At the moment, our modules are very small.
Small for now, but the plan is to scale up. In fact, all of the technologies the C4Value people are developing will be scaled up and integrated into a mobile testing facility they call Moving Lab.
So what's the plan for this Moving Lab?
Sandra said all of the gear will be collected and assembled in a mobile lab, and the lab will go in a shipping container and sent off to be tested at a real-world desalination plant in the Canary Islands. The plan is to evaluate all the technologies on a number of brine streams at that location.
Wow, that is really cool. But we're coming to the end of our story here. So what did these researchers tell you about what the future of seawater mining could look like?
Yeah, that's a great question. Everyone I spoke with was so full of energy, but very realistic about large-scale implementation being pretty far down the road. And it's also important to remember that while this research is primarily based out of labs in the US and EU, the technology these scientists are developing could have global implications. So I'd like to leave you with something Chinmay said about her hopes for the future.
We need to think about seawater as an equitable resource. I think it's very important to not be bogged down by the fact that it is low concentration. We need to think creatively about how we put different technologies together so we can make it a more economically viable option.
It leaves me feeling cautiously optimistic about the real-world benefits we could all share from the oceans that connect us.
This episode of Stereochemistry was written by Mitch Jacoby, with audio editing by Feuer DiTusaStory. The episode was produced by Kerri Jansen and me, Ariana Remmel. Full credits for this episode are in the show notes. Stereochemistry is the official podcast of chemical and engineering news. C&EN is an independent news outlet published by the American Chemical Society. Thanks for listening.